All right, these are the notes for the gas law unit that we're going to do. Because of the software that I'm using, I'm limited to 15-minute long videos. So we'll be doing a few sections at a time. It's possible we could get through all this in about between 45 and 60 minutes. All right, here we go. So you should have already downloaded and printed all of your notes, or at least downloaded so you can make electronic notes in the blanks. First thing we're going to talk about, this is chapter 10 in the book that they are using. It's chapter 5 in our book, but don't worry about that at the moment. All right, first question or first section. We want to name 3 characteristic properties of gases that are mentioned in the section, and you should be reading the book. If you don't have the book broken out, you should have that with you. All right. The 3 characteristics about gases: they expand to fill a container, they are very compressible, and they form homogeneous mixtures with other gases in the container in all proportions. Now, I'll back up for a moment and say, feel free to stop this video at any time so you can write down notes. The object here is to get your notes completed so you know what's going on. Part B, or section B, these properties of gases can be explained by the fact that gas particles, they're relatively far apart from each other, and that's going to be key to what we're going to talk about at the end, which is the kinetic molecular theory. Now, the first thing we want to do is talk about the definition of pressure. If you have already taken physics, you probably know this. If you haven't, then you don't. Pressure is the force per unit area. Force is measured in newtons or kilonewtons, possibly even meganewtons, and area would be measured in square meters. Atmospheric pressure can be defined as the force exerted by the atmosphere on any given surface area. Now, back a long time ago in the 1600s, an Italian man by the name of Evangelista Torricelli was able to prove that air does have weight, and he invented the barometer, which is illustrated in this picture that you see. At the time, they didn't know that mercury was poisonous or really hazardous long term. It's not poisonous immediately, but mercury was relatively easy to obtain. He got a little pool of mercury. He inverted a glass tube that was closed at the top of this picture, open at the bottom, put it into the mercury. The atmosphere pushed down on the mercury, and it caused the mercury to go up inside the tube to a certain height, h. And as the pressure of the atmosphere changed, the pressure or the height of this liquid level of mercury would change. So we've got a lot of units that we can use in chemistry. There'll be 3 main units that we use. Those are atmospheres, millimeters of mercury, and torr. A millimeter of mercury is exactly what it sounds like. It's the height of a column of mercury in a glass tube measured in millimeters. 1 atmosphere, the standard atmospheric pressure at sea level, is 760 millimeters of mercury. So the column of mercury that would rise up in this tube was 760 millimeters high. And 1 millimeter of mercury is named after Torricelli, and that's abbreviated as a torr. So 1 millimeter mercury is equal to 1 torr. 760 millimeters of mercury is 760 torr, and that's equal to 1 atmosphere. So now we've got a little problem here on the right. We've got a pressure of a gas. It's coming up out of this flask or this container, and it's pushing a column of mercury up, and we want to know something about the pressure of the gas in the sealed flask. So the question says, the diagram at the right shows an open-end mercury manometer. Suppose the atmospheric pressure in the laboratory is equal to 764.7 torr. Is the gas pressure in the sealed flask higher than that or lower than that? And how do you know? Well, of course, the answer is that it's higher than that. And the reason is that we can look at this diagram and we can see that the mercury level on the side closest to the flask is lower than it is on the side open to the atmosphere. What that means is that the pressure inside the container is pushing harder than the atmosphere is pushing. And so the pressure inside this container must be higher than atmospheric pressure. Well, then, of course, the next question is, how much higher? How do we determine what that number is? And we can do that by looking at the difference in height of the two legs of mercury on the left side and on the right side. We can see that one of them is 103.8 millimeters, and on the right side it's 136.4 millimeters. And if I take the difference in those two numbers, I get 32.6 millimeters of mercury. Well, that plus the atmospheric pressure of 764.7 torr comes out to be 797.3 torr, which we know is greater than 1 atmosphere. So we do a little unit conversion. We multiply by 1 atmosphere divided by 760 torr, and we get 1.049 atmospheres. All right, if you were to transport the open-end manometer shown in the previous picture to the top of a mountain, what would happen to the value of H, the height of the column of mercury? Would it remain the same? Would it decrease? Or would it increase, and why? Well, the answer is that it increases because atmospheric pressure would be lower up at a higher altitude. So the delta P, the difference in pressure between the contents of the flask and the outside atmosphere, goes up. It increases. And that causes that height difference to get even larger. All right, now we're going to start talking about some of the gas laws. First gas law is Boyle's law. An English guy by the name of Robert Boyle discovered that when the pressure on a fixed sample of gas is doubled, the gas volume is cut in half. All right, now we see we've got this little table of data and a little graph down here. We've already got two pieces of data. We've got pressure of 1, that's at 10 atmospheres, and the volume of a second data point was at 15 milliliters. Well, I can look at this and I can fill in the data, and I can see that when the pressure is equal to 10 atmospheres, what is my volume? And likewise, I can look at these two pieces of data that are already on the graph, and I can see when the volume is 50, my pressure is 2. When my volume is 25, my pressure is 4. And I can look at this data and I can read the other two data points. I plug in and I can see when I look at this data, I can see that this in fact is not a linear function. It's an inverse relationship function. It's a 1 over x function. And I can see that when I plot this data. All right, I can't really draw in a curve that would be in any way accurate, but you can see for yourself that this is going to be an inverse function, okay? We call this relationship between pressure and volume an inverse relationship because as one goes up, the other goes down. All right, so we've got another relationship called Charles' law, discovered by Jacques Charles. I'm sure I'm not pronouncing that correctly in French, but oh well. C'est la vie. Jacques Charles discovered the fact that the volume of a fixed sample of gas at constant pressure will increase when the temperature of the gas is increased. So now I've got another little table of data, and if you have this printed, what I encourage you to do at this point is to stop this playback, lay out a straight edge, and line up those 4 points on this graph from upper right to lower left. and draw a line down through the lower left-hand dot and see where it intersects the axis, okay? Because the answer to that, when we do that, we get to answer the question, at what temperature would an ideal gas have a volume of 0? Okay, so if we lay out a ruler, a straight edge, and we draw a straight line, we get a number that looks like it's about minus 275 degrees Celsius. Well, in fact, if we were really, really careful about that, we would see that it is in fact minus 273 degrees Celsius. And very, very careful measurements with very, very expensive equipment has shown that absolute zero is equal to minus 273.15. In AP Chemistry, we will never need these 5 significant digits. We will restrict ourselves to the value of minus 273 degrees Celsius, and that will be considered to be absolute zero. All right, let's look at the statement at the top. If a 1 liter sample of hydrogen gas at 25 degrees Celsius is heated to 75 degrees Celsius at constant pressure, the volume of gas should increase to 3 liters. Is that true or not? Do you agree or do you disagree with the statement above? Either way, you need to justify it by doing some sort of calculation. And of course, if you've had any first-year chemistry class, you know that that is not a true statement. I have shown that I have the circle over agree, but in fact it's disagree, because this is in Celsius and the real way we deal with temperature is in Kelvin, not in degrees Celsius. So I can look at this and I can say 1 liter divided by 298 K is equal to V2 divided by 348 K. And so I see that my real new volume, instead of being 3 liters, is in fact only 1.17 liters, because the temperature has not tripled. We must do this in degrees Kelvin. And the reason we have to do this in degrees Kelvin is because we need a temperature scale that does not go negative. Because if we didn't have that, we would end up with negative pressures and negative volumes to go with negative temperatures. And clearly that doesn't make any physical sense. So we have to work our degrees, our temperature scale in degrees Kelvin. All right, number G, or letter G. Joseph Louis Gay-Lussac observed the law of combining volumes, and based on this law and our knowledge of stoichiometry, we would predict the following results at constant pressure and temperature. You can see by the first reaction to the right that 2 moles of hydrogen plus oxygen reacts to form 2 moles of water. So we would expect 2 liters of water vapor. And likewise, if I had 1 mole of nitrogen and 3 moles of hydrogen to form 2 moles of ammonia, I would expect that I should get, according to the stoichiometry, 2 liters of ammonia gas. All right. Amadeo Avogadro interpreted these observations, and he proposed that equal volumes of gases at the same temperature and pressure contain the same number of molecules, and this is called Avogadro's hypothesis. So we are going to stop here because my time on this video is drawing to a close. I will pick back up in part 2 of this video on this slide.